Alright, now we go to the introduction. So, background of agent value in engineering system. To begin, agent values and agent vectors are fundamental mathematical tools used to analyze the dynamic behavior of structures and mechanical systems. In engineering, they help us understand how systems respond to vibration, forces, or other time-dependent changes. One important application of this finite element model updating, or FEMU. FEMU is a technique used to improve analytical model so that they match real-world data, especially vibration measurement taken from physical structures like buildings, bridges, or machines. This process is extremely important because in structural engineering, inaccurate models can lead to unsafe designs, performance issues, or even financial losses. So by using FEMU, engineers can make sure that their models are not just theoretical but actually behave like the real structures they represent. And now, why is this application relevant to our project? In FEMU, engineers use a method called inverse agent sensitivity analysis to calculate how model parameters, such as mass and stiffness, should be adjusted. This is done by comparing measured data with prediction from the original model. The corrections are often calculated by solving system of differential equations, where agent values help show how sensitive the system is to those changes. FEMU has many important uses, such as damping design, structural health monitoring, and optimizing large-scale structures like towers or bridges. In all of these cases, it has made structures safer, more reliable, and more efficient. In our project, we explore the mathematical foundation behind FEMU and show how linear algebra and differential equation play a critical role in improving structural model.
Now, let's move into the core methodology of our project, the mathematical formulation of finite element model updating. This process involves two main parts, the derivation of equation and the solution method used to update our model. The purpose of finite element model updating is simple but powerful, which is to update and correct parameters in a finite element model. These parameters, such as a mass, stiffness, are adjusted so the simulated vibration match what we observe in experiment. By doing this, we can improve model accuracy, which is critical in engineering design and safety. Here is a step-by-step breakdown how finite element model works. First, we define a correction vector denoted as delta P. This vector contains all the unknown parameters changes that we want to find. This could be changes in stiffness or material density. Then we move to the sensitivity matrix, which sits on the left side of the equation. This matrix tells us how sensitive our model data. That is the eigenvalue and eigenvector, which is changes in each parameter. On the right side of the equation, we have the model data error. This is the difference between what we measure in real-life experiment and what our model predicts. It tells us how far off our model is from reality. To solve this, we use the least squares method. Because our system has more equations than unknowns, least squares help find the best solution that minimizes the overall error. So basically, this is the best compromise between all the data points. There are two versions of finite element model updating analysis, which is the single mode case and the multiple mode case. Here is the differences between the single mode case and multiple mode case. The single mode case only uses one frequency and one mode shape. It is minimal and works well when data is limited, like in early stage analysis. On the other hand, the multiple mode case uses several modes, for example from the first to the L modes. This gives a more detailed and accurate update of the model, and is generally preferred when more data is available, and the results are far more reliable.
Okay, now let's proceed to the results and discussion part, which will go to the interpretation part first. Okay, this slide we can show that the result prove that eigen derivatives are effective in guiding structural model updates. They help pinpoint which elements in the model need the changes. Okay, this This approach also is efficient, accurate, and works well even when the full data isn't available. So, it's suitable for use in engineering fields like civil, aerospace, and mechanical design. Okay, for now, the next slide is analysis of results. The FERMO method was applied to a 300-element beam model, where the experimental model data, which is frequencies and mode shapes, were used as a reference. Okay. The model was updated using eigenvalue and eigenvector derivatives to identify the sensitive design for parameters. So, which is we use two sets for tested. Okay, the first set we use 4 modes, which produce 0.1 to 0.3% error, while when we use 10 modes, it produces 0.01 errors, which is more accurate. So as we can see here, that even with fewer modes, the FEMO approach still reduces the errors significantly.
So moving on to the importance of FEMU in real-world application. Firstly, FEMU provides structural safety by helping us prevent resonance by identifying natural frequencies that could lead to failure. Secondly, it helps us to get accurate simulation by enhancing the realism of finite element models using real-world vibration data. Thirdly, we could get predictive maintenance by detecting internal damages early by monitoring changes in vibration characteristics. So in conclusion, differential equation and eigenvalue analysis are essential for comprehending and forecasting the behavior of real-world systems. These powerful tools connect theoretical concept to practical application, enhancing structural safety and optimizing design. As a result, they are essential to achieve a smarter, safer, and more efficient engineering decision.